Hi, my name is Adrienne Watts. I'm joining today from Indianapolis, Indiana, and I'm going to talk about streaming real-time flight data. This session is a case study in aviation data processing. Again, my name is Adrienne Watts, VP of Data and Analytics for Mosier Consulting. I have a passion for all things data and helping organizations achieve measurable results. Today, we'll explore streaming real-time flight data utilized by the FAA. Many people have tracked a flight at some point in time. You may have done this by visiting a website or using an app on your phone to follow the flights of friends or family or colleagues. Maybe you're tracking it to know when to pick someone up or to watch for delays. A quick Google search will return multiple options for tracking. FlightAware, Flight Tracker, and Flight Radar 24 were some of the first results that appeared when I did a search. What most people don't know is that the flight data is publicly available, and information on many of the data sources is documented on the FAA website, faa.gov. My team recently had a use case to partner with a company in the aviation industry to process flight data, and this was an interesting and compelling project with fascinating data sources to be ingested and analyzed in real time. Flight information doesn't come from a single source. It includes data pieced together from different sources of publicly available information, including registration information from the Federal Aviation Administration and broadcast signals from the planes themselves, which are known as ADS-B data. Here are 4 key data sources and processes for integrating flight data. ATC radar provides positions and flight plan information from air navigation service providers. It also provides flight plan information, including real-time departure, arrival, and delay information, as well as flow management and delay program messages. SWIM is the system-wide information management program which facilitates the data sharing requirements, providing the digital backbone for NextGen. SWIM is designed to facilitate greater sharing of system information, and the mission is to standardize, enhance, and optimize the secure exchange of relevant information, data, and services to enable operations for the aviation community. Next, multilateration, or MLAT, is the use of mathematical calculations to derive positions for aircraft that are not yet transmitting their exact position via ADS-B. We can determine the positions of many more aircraft than we would otherwise be able to track using this technology. Fourth is ADS-B. Real-time ADS-B is now the preferred method of surveillance for air traffic control, and we will do a deeper dive into this data. What is ADS-B? At the highest level, it's a system used to track aircraft in the sky. It's broadcast directly from the aircraft themselves, and it is currently the primary technology used to receive live flight information. An aircraft in a controlled space in the United States is required to be equipped with a transponder to broadcast information, including its location, speed, altitude, and a host of other data points which are transmitted over an open network, such that anyone with proper equipment can access. As depicted in this image from iFly America, this is impactful because it's not just communication from an air traffic control tower to individual airplanes. With ADS-B, everyone with a transponder is both transmitting and receiving signals. It does include the air traffic control tower to ground stations and ground stations to aircraft, but it also includes broadcasts from aircraft to other aircraft directly, increasing awareness to the pilot of any other airplanes in their vicinity, increasing safety, and improving collision avoidance. And a fun fact is that it also includes crowdsourced data from aviation hobbyists all over the country and around the globe who have the right equipment. Any hobbyist hosting a transmitter is receiving and sending signals. For example, sharing that an aircraft is descending and plotting its GPS location every half second. With all this data being broadcast from a large number of crowdsourced transponders, it gives a fairly accurate real-time picture of where planes are. And this is not limited just to commercial aircraft, but it also includes private planes and other aircraft such as some drones authorized to fly in controlled airspaces. As you can imagine, the resulting volume of data is a challenge to stream in, let alone analyze in real time. What does ADS-B stand for? It stands for Automatic Dependent Surveillance Broadcast. Automatic because it doesn't require any work from the pilot or controller. The signal is automatically broadcast out every 1/2 second. Dependent because it depends on gathering data such as position and altitude from the plane's GPS and other systems. Surveillance because this information is used for surveillance, helping controllers and other pilots surveil and track airplanes in the sky. Broadcast because it transmits the information available to anyone with the appropriate receiving equipment. How does ADS-B work? First, each aircraft has a transponder, which is broadcasting its location, speed, altitude, and other information over an open network to ground stations and other aircraft. At the same time, it also receives information from other aircraft, including their unique identifier, GPS position, altitude, and heading. The receivers process data for display on cockpit screens or air traffic control screens. There are some limitations with this technology. For instance, it can be broadcast for a distance of 250 nautical miles in all directions, and it needs an unobstructed line of sight. This makes coverage difficult near mountains or over oceans. There is space-based ADS-B to help increase coverage. There are satellites circling the Earth with receivers to collect ADS-B data. They are carrying a system developed by Aviation, which captures the aircraft information and relays to aircraft and ground stations, allowing more global coverage in near real time. And finally, this technology is continuing to grow and evolve, and the number of aircraft equipped with receivers will continue to increase. Space-based ADS-B enables surveillance over oceanic airspace through receivers hosted on satellites and across the entire globe. With the space-based concept, aircraft may be tracked anywhere they fly in near real time, increasing safety and efficiency for all users. The Ariane ADS-B network is hosted on the new state-of-the-art Iridium NEXT satellite constellation, which consists of 66 low Earth orbit interconnected satellites. The space-based ADS-B network provides position updates anywhere in the world and eliminates coverage gaps over oceans, deserts, and polar regions. With satellite coverage, availability exceeds 3 nines, and the typical life cycle is 14 years. This technology is being increasingly used across the globe and will continue to impact the aviation industry. Prior to ADS-B, radar was one of the main methods of determining location. Radar relies upon bouncing radio waves off an object like another airplane. ADS-B has several advantages over radar. Better visibility. ADS-B ground stations are smaller and can be placed in locations that radar towers cannot. Improved situational awareness. This means that pilots have greater awareness of other aircraft nearby and can better navigate mid-flight situations. Enhanced air traffic control. ADS-B equipment provides air traffic control with updated aircraft information almost every second, while radar can take 5 to 12 seconds to update an aircraft's position. Environmentally friendly. ADS-B is environmentally friendly technology and it supports environmental research. There are a large number of hobbyists and plane spotters sending and receiving ADS-B data. They might like to know what planes are overhead, or there are various kinds of enthusiasts with an interest in the data. This group often leverages a Raspberry Pi and runs a program such as Flight Radar 24, which picks up the transmitted information from nearby aircraft. This technology will perform both local data collection and then publish that data to the shared service. Thus, if you are a provider of the data, by hosting a transponder, you also gain access to the streams. These hobbyists contribute to the coverage and data as a part of the ADS-B network. There are numerous use cases for ADS-B data, and today I'll share some for both federal and commercial uses. We've highlighted how ADS-B data improves situational awareness by helping pilots see beyond their physical line of sight. It also provides better ATC traffic flow management and enables increased capacity and efficiency by supporting merging and spacing, self-separation or station keeping, enhanced visual approaches, closely spaced parallel approaches, and reduced spacing on final approach. The use of ADS-B data leads to improved collision awareness by helping pilots to see and avoid other aircraft, providing real-time cockpit airspace display, and improving cockpit final approach and runway occupancy. It can assist with accident investigation and provide more accurate search and rescue response. Weather data integration provides VFR-like separation in all weather conditions and real-time cockpit weather display. It improves surface operations in lower visibility conditions and provides near visual meteorological conditions, VMC, capacities throughout the airspace in most weather conditions. Environmental impact. ADS-B data supports analysis of the potential impact of space-based technology on global aviation carbon emissions. Researchers have estimated that approximately 14.3 million metric tons of CO2 can be prevented from entering the atmosphere between the years of 2020 and 2030. This is primarily from gaining efficiencies with oceanic and remote airspace routes, which lack radar coverage and operate under separate procedures compared to other airspaces. Due to the lack of real-time surveillance in those regions, air traffic control separates aircraft by approximately 50 nautical miles. This means that they have to take longer or higher routes, which is inefficient and comes with a heavy emissions cost. With the addition of space-based ADS-B, ATC can use more precise locating capabilities and enable optimum altitudes, speeds, and routes, significantly decreasing harmful effects on the environment. There are also many commercial use cases. We can envision how this data greatly improves flight tracking and delay prediction. It can also be valuable for research purposes, such as studying aircraft performance, air traffic patterns, and developing new air traffic management strategies. Airlines can use ADS-B to monitor their own fleet operations, track aircraft positions, and optimize flight planning and scheduling. This data can also be used for post-flight analysis and performance monitoring. Airports can use ADS-B data to improve ground operations, such as monitoring aircraft movements on the tarmac, managing gate assignments, and tracking aircraft positions for better resource allocation. Companies involved in air cargo and logistics can use ADS-B data to track the location and status of cargo flights, enabling better planning and coordination of operations. There are numerous ways in which ADS-B data is used in official capacities. But next, let's share some unofficial ways in which consumers are using the data. There are official and legitimate websites and apps that track commercial flights and publish it to provide consumer insights. But since it's publicly available data, that same data can be scooped up by virtually anyone looking to follow private planes with celebrities and other public figures too. So there are aviation enthusiasts and Raspberry Pi enthusiasts who contribute to the ADS-B data stream significantly and provide value by expanding the network. But also, there are some unexpected consumers. Elon Musk and Taylor Swift have both expressed challenges with their private jets being tracked, and also impacted politicians and other public figures. Next, we will talk about an industry use case and how one company is streaming ADS-B data. We have a client in the aviation industry with a need to ingest real-time flight data for integration with their software. Additionally, in order to receive ADS-B data, this client hosts a Raspberry Pi. Their original solution was implemented using a .NET application to write to an on-prem server, and they were experiencing several challenges. Performance issues, including long-running jobs and failed jobs. They were running out of space, had to delete raw data frequently because they didn't have storage. Messages were being received and processed out of order. And the app was taking so long to process at times that they were only processing it once a week. As you can imagine, it's not trivial to coordinate multiple streams, turning streams from multiple data sources into one flight record. Original and destination airports, flight time, arrival time, maps back to actual raw data, where you can get all these points in one time, have to be merged into a single record of truth. When evaluating how to address their challenges and re-architect the solution, there were many considerations. Data profiling and analysis. We needed to perform a thorough analysis of each data stream to understand the data structures, formats, and quality issues. We needed to identify missing values, outliers, duplicates, and inconsistencies within each stream, and then assess the compatibility and consistency of data types, units of measurement, and coding standards across streams. Data transformation and cleansing. This included implementing data cleansing rules and transformations to standardize data formats, handle missing values, remove duplicates, and correct errors or inconsistencies. Using technologies like parsing, data type conversions, regexes, and lookup tables to bring data into a consistent format. Data validation and quality rules. This included defining and enforcing data quality rules and constraints to ensure that merged data adheres to business rules and data integrity requirements. Also, there's a need to implement validation checks such as range checks, pattern matching, cross-field validations, and referential integrity checks. Metadata management. The solution needs to maintain comprehensive metadata that describes the data sources, transformations, quality rules, and business definitions, and use metadata to document lineage, track changes, and provide context for downstream data consumers. Data mapping and integration. One requirement was to establish a common data model or schema to serve as the target for the merged data, and to ensure the ability to map and transform data elements from the multiple streams into the common data model, ensuring consistency and integrity. Data lineage and auditing. One goal was to implement data lineage tracking to understand the origin and transformations applied to each data element in the merged data set. Additionally, the solution needed to maintain audit logs and versioning to track changes, identify issues, and enable data recovery or rollback if needed. And finally, continuous monitoring and improvement. The need to continuously monitor data quality metrics and issues in the merged data is significant. The solution should establish feedback loops and processes for addressing data quality issues, and regularly review and update the data quality rules, transformations, and mappings to maintain data consistency and integrity. Next, we'll talk about the nature of the data. For this project, the client was integrating 3 primary streaming sources, one of which is the ADS-B data. Today, the client is streaming 92,000 daily flights and approximately 20 million records per day from these sources. Next, let's talk about implementation. The solution implemented for the client leverages Snowflake and evaluated the use of Snowpipe and Snowpipe streaming. Additionally, instead of a custom build-out, the client used a managed data and analytics solution called Honeycomb Analytics, which is powered by Snowflake. And this exact solution is a custom build solution for many organizations. Why was Snowflake chosen? Scalability. Snowflake can handle large volumes of data and can scale up or down as needed without significant reconfiguration. This makes it suitable for streaming data, which can have highly variable workloads. Performance. Snowflake's architecture allows for high performance with features like automatic scaling, data partitioning, and efficient query execution. This ensures real-time or near real-time processing of streaming data. Integration. Snowflake integrates well with various data streaming platforms and services like Kafka, AWS Kinesis, and Apache Spark. This makes it easy to ingest and process streaming data from multiple sources. Data sharing and collaboration. Snowflake's data sharing capabilities allow for easy and secure sharing of data across different teams and external partners, which is beneficial for collaborative analysis of streaming data. Unified data platform. Snowflake provides a single platform for handling both batch and streaming data. This unification simplifies the data architecture and allows for more seamless data management and analysis. Security and compliance. Snowflake offers robust security features, including data encryption, access controls, and compliance with various regulatory standards. This is critical for companies handling sensitive or regulated streaming data. Cost efficiency. Snowflake's usage-based pricing model allows companies to pay only for the resources they use. This can be more cost-effective for handling intermittent or variable streaming data workloads compared to traditional fixed-cost infrastructures. Ease of use. Snowflake's user-friendly interface and SQL-based querying make it accessible for data engineers and analysts, reducing the learning curve and improving productivity. These advantages made Snowflake a compelling choice for our client looking to handle streaming data efficiently and effectively. A data flow diagram of the architecture implemented for this client looks something like this. On the left-hand side, there's a list of data sources, including the ADS-B stream and 2 FAA sources, SFDPS and TFMS. And a fourth icon is there to represent other data sources, as it's common to merge numerous data sources together when building out your flight model. This implementation leverages subscriber microservices and Snowpipe to move to a raw, trusted, refined architecture within Snowflake. The outputs on the right-hand side include reporting and data visualization, downstream files, and a web application which shares the data with the client's customers. Snowflake offers 2 methods: Snowpipe, the original offering, which leverages pipe, and the newer offering, Snowflake Streaming, which allows direct data streaming, sending row sets over HTTPS using a client SDK. Snowpipe Streaming offers exactly once and per channel ordering, which means you can stream data over a logical named connection to Snowflake, which allows you to get the data once and process the order. Achieving exactly once delivery can be challenging, and Snowflake has documented best practices for custom code, such as to ensure appropriate recovery from exceptions, failures, or crashes, you should always reopen the channel and restart ingestion using the latest committed offset token, and use the last committed offset token provided by Snowflake as the source of truth and reset your own offset accordingly. Channels. The API ingests rows through one or more channels. A single channel maps to exactly one table in Snowflake. Multiple channels can point to the same table, but the ordering of rows and offset tokens are only preserved within a channel, not across channels that point to the same table. Snowpipe Streaming offers high throughput, supporting up to gigabytes per second per table. This is a low latency feature. Data is queryable seconds after acknowledgement. You can configure the latency using the option max client log. The default option is 1 second, and the maximum can be set up to 10 seconds. Next, low overhead. Low overhead refers to that minimal configuration and setup is needed to use this feature and functionality. And finally, low cost. This architecture results in lower load latencies with corresponding lower costs for loading similar volumes of data, which make it a powerful tool for handling real-time data streams. And in conclusion, the client has a performant and scalable architecture. We've eliminated all the challenges from the previous solution with the process failures and messages processed out of order. Large volumes of data are able to be sliced and diced along different axes in real time. And reporting and analytics are produced across a number of different technologies, including a web app and data visualization. I hope you enjoyed learning about real-time flight data. Now everyone can get a Raspberry Pi and start processing their own flight data. Thank you for your time.